So we're going to do a pre-lecture video covering aspects of one-dimensional motion. So far we've been dealing with average accelerations and average velocities, and so today what we'd like to get to is be able to discuss more instantaneous values. So objects rarely travel for long with a constant velocity, and so it's much more common that the velocity changes, and so average velocities can be useful, but a lot of times you'll want to be thinking about the instantaneous velocity. And basically, we all know this. It's just like watching your car's speedometer, right? So your car's speedometer changes. That would be the instantaneous velocity. Mathematically, the average velocity becomes a better approximation to the instantaneous velocity as the delta t gets smaller and smaller. And so that would be taking the limit as delta t goes to 0, and you get that the velocity is the derivative of position with respect to time. Now, a lot of textbooks, what they'll do is, typically for position, we'll use variables like x, y, and z. And so what they do is kind of a dummy variable to cover all of those. They just call it s. So whenever there's an s, we're just sort of thinking that that is one of the dimensions, and they're just trying to sort of keep it more general. And so here's a question about instantaneous velocity. So take a second on this one here, and the question is, when do objects 1 and 2 have the same velocity? So we got a plot of the position versus time for these two objects. So go ahead and think about this one, and then we'll talk about it. All right, so hopefully you got that it's A. And so the trick here is that we just learned, okay, and so this is some situation where we're trying to find the instantaneous velocity. And so this is the case. So again, we use s's here, but in this particular case, we're going to do it for the x direction. So we can sort of, in that dummy variable, put in dx dt. And the idea here is that the slope of the tangent line gives you the velocity, instantaneous velocity for these objects here. And so if you look over here, right, you can take the slope of the tangent line at any point for this curve here, and that gives you the instantaneous velocity. And the point right around in here or so is where the two slopes are the same. So if you remember, we sort of discussed it. At this point, we're going to focus a lot on 3 different kinds of motion. So this motion here is a constant velocity. So this is just, you're moving along at a constant velocity. And so hopefully you notice that the slope is the same. So the instantaneous velocity is the same the whole time. This one here, take a second and think about this. This is either something that's slowing down or speeding up. What do you think? All right, so hopefully when you look at that, you agree that that would be something that's slowing down. And so you can just look, like here, if you take the tangent, the slope of the tangent line at this point here, it's much steeper than this one over here. And if you look over here on this side, it's going to be even less steeper. So the velocity for this particular thing here is getting smaller, right? And so it's going to be slowing down. So this would be the kind of motion where the acceleration is in the opposite direction of the particle's initial velocity. And then if we were to go through and do this again, I'll just change colors so it's a little bit easier to see. That's a bad one. And so then here, something kind of like this. Again, I'm having them go through the same point, but it doesn't really matter. But this would be something where your object would be increasing its speed. And if you pick a couple points here, like here's the slope of the tangent line there, there's the slope of the tangent line there. Hopefully you can see that the slope of the tangent line gets more and more steep as we go on. And so this is something that we'll practice lots with, but this is sort of our introduction to it. And then by that same token, so we just sort of saw how you can find velocity from position. Well, you can also find position from velocity. And so suppose we know an object's position to be, again, they're going to use this dummy variable s1, which could stand for x or y at some initial time, t initial. We also know the velocity is a function of time between ti and tf. So we know the velocity. And so even if the velocity is not constant, what we can do is we can divide it into little tiny steps, right? And basically, if we take, sort of our best guess of sort of the instantaneous velocity at some moment times some little delta t, that's going to give us a distance. Okay, you can just do it by dimensional analysis. This would be meters per second times time ends up in meters. And so what this equation here is this is like our initial position. And what we do is we take our velocity and break it into little tiny pieces where it's velocity times some delta t. And that gives us a really good approximation to sort of how much distance that object moves in that little tiny bit of time. And the thing is when you take this to its extreme, delta t goes down to 0, then this limit is going to end up being an integral. And that's what this symbol is. It's our integral. And so the expression on the right, you can read it as the integral of vs dt from ti to tf. And here's just a graphical way to look at that. So again, here we have our velocity as a function of time. And so what we can do is this curve here, we can kind of break it down. Now let's imagine if we had a very simple case, for instance. Okay, so imagine this is our velocity and this is our time, and we wanted to know, so this is like, some our velocity initial, and it stays constant, and then some total time, maybe t final over here. And so if we want to know how much distance this thing gains, what we would do is just take that velocity times the time. Well, hopefully you can notice here that that would be this area under the curve, and that's kind of the point that we're getting at here, is that in a situation like this where the velocity is constant, it's just a case of basically taking this area. Now in a situation over here where the velocity is changing, we can't do something nice like this, but what we can do is we break it into little pieces, right? And these little pieces, you can think about their volume as being volume times, velocity times delta t, which is again in meters. And so what happens here, and hopefully it kind of makes sense, like right here you're starting at a smaller velocity, so there'll be a smaller area under the curve here, right? And then this next one is a little bit higher of an area under the curve. The velocity is increasing, and so because the velocity is changing, you're going to be increasing the amount of meters you're adding on every second. And then of course it goes down to this point where the velocity gets really small and you're barely adding on anything at all. And so the geometrical interpretation of this, and I think I said volume earlier, I apologize, that this is the area under the curve, is that basically you can think about as your position final equals your position initial plus the area under the velocity curve between the times that you're interested in. And so we can lead ourselves to a question kind of like this. So go ahead and pause here, think about this, and we'll talk about it. All right, hopefully you had time to think about this one. And for me, I came out with 12. And so let's go through and do this. And so again, the idea here is it's the area under the curve. And so you got to go through and look here. And so the area, for each box of area, okay, so each box, it's got a height of 2 meters per second and a width of 1 second. And so if I take that area, again, this is kind of 1 meter per second times 1 second equals 2 meters. So every block of area is 2 meters. And so if you look here, 1, 2, 3, 4, 5. Now this one and this one is basically 2 half, and so it's 6. So 6 times 2 gives you 12. Another way to just kind of visualize this a little bit. So again, we're looking for delta x. And so if you think about it, for this first period, for the first 2 seconds, I'm going at 4 meters per second. So 4 meters per second times 2 seconds. All right, and then over here, it's like this triangle. And what's happening is at this point, my velocity is decreasing down to 0. So I'm not going to go, again, another 4 times 2. But what I do is I go 1/2 4 meters per second times 2 seconds. Again, that's the area under the curve. But what it is it's because I'm slowing down there, I don't gain as much ground every second. And so this is another way to kind of visualize it. So 8 meters, and then here would be 8 divided by 2, which is 4, equals to 12. And so that's just a graphical way to understand how you can get position from velocity. Now, we're going to move on and look at the case when there's constant acceleration. So I just want to sort of specify that's really important. We'll use this so much that you can almost get to the point where you think it always works, but it really, it only works when there's constant acceleration. But this does handle many different kinds of applications. Like for instance, for us, gravity and friction will be forces that in 2A will be constant, right? And there's other forces that'll work that way too. And of course, a constant acceleration will it derives from a constant force. And so what we can do here is take our acceleration average equation, which of course if the acceleration is constant, you can just call that the instantaneous acceleration. It equals delta v over delta t. We can write that out sort of the way we would like to. And now what happens is we're almost always going to call the initial time to be 0. You don't have to, but it just saves you so much grief. Okay, so we're just going to get rid of that guy. And then here, if I solve for this, this is the first of what we call our kinematic equations. Kinematic equations for when acceleration is constant. And so we're gonna sort of develop them here, and then we'll in another video we'll start sort of practicing with these. But this is the first one, and so this gives us the final velocity in terms of the original velocity times if we know our acceleration and our time. All right, so we've got this equation. This is the velocity equation for constant acceleration. Again, in this equation, a and v0 are constants. The acceleration and the initial velocity, and if you happen to know the time, you can plug it in and find what the final velocity is. Now there's another way to derive this, and that's using this relationship here, that the acceleration is the first derivative of the velocity with respect to time. So we had discussed how the velocity is the first derivative of the position. Oh, the acceleration is the next step. And so in a very similar way, the acceleration is the slope of your velocity versus time graph. And what we can do is we can move these differential pieces of this derivative around in a way such like this. And so I can write this here like this here. And so what this is the change, the sort of small incremental change in the velocity is going to equal that sort of instantaneous acceleration at that point times the small incremental change in the time. And what we're able to do is sort of take these relationships and integrate them. And so these are little tiny pieces. And so what we typically would do is for the velocity, we'll integrate from our initial velocity to our final velocity. And then for the time, again, we almost always call the initial time 0. And so then the final time we'll just write as t, just to kind of make life a little bit easier. Now these integrals are, in this case here, it's just the integral of dv. And so what you get for that is you get the velocity evaluated from the points v final and v0. And now over here, I can pull the acceleration outside because it's constant, and I get the same thing over here. So it's sort of the easiest integration we can have. If it's just the integral of the dt, the antiderivative is just t. And so you get a, t, and again, this is evaluated between 0 and t. And so here I get my v final minus v initial. Excuse me, let me write that a little bit better. V final minus V initial. Then over here I get just A times T. And so that's just another way to write it out using calculus. But again, it's our constant velocity equation. And here would be a graph of one of those. So sort of a, imagine in this case here, my object started with some initial velocity of 1 meter per second, or actually here I'm doing centimeters per second, and it's got some constant slope, which is that acceleration, right? And so again, because we know that the acceleration is the dv dt. But this is what your line would look like here. And so what you'll see when you're dealing with, again, constant acceleration situations is the velocity versus time graph is going to be linear. Now, it could go the other way. I could have made it negative acceleration or something like that. Or if the acceleration is 0, it would be a flat line, but it's going to be some linear line. So when you have constant acceleration, they're going to be giving or taking away speed at a constant rate every second, and you'll get this nice, again, linear line here. So we've got our first kinematic equation. Now you want to get our second. So the first one dealt with velocity. The second one is going to deal with position. And so suppose we know an object's position. Again, we use this sort of dummy variable of SI at some time ti. Now if it's got a constant acceleration, then it's going to have a really flat constant acceleration picture like this, which we just discussed, that is going to give us then a nice linear velocity versus time graph. And we know that the area under this curve is going to give us the distance that we traveled, right? And so we take this equation. So we have SF over here, equals SI. And so what we can do is we can break this area under the curve into two pieces. There's this first piece here, and so if we pick just two random points here, We're calling them v initial in the s direction, v final in the s direction. So we can sort of think of this part here as just a little rectangle. So this area would be a height of vis, the initial velocity, and then times the amount of time that we're spending. So plus, so vis delta t, just like given here. And then over here, from our previous equation, we know that a times the change in the time is going to be that difference in velocity. And so the area for this piece here is going to be a triangle where it's 1/2. The height is going to be as times delta t, and then the base would be delta t. And so we get this term 1/2 as delta t squared, which is this piece over here. And so this is our position kinematic equation. Again, real important that when you're going with constant acceleration is when this is valid. And so this is how I would write out this equation. And again, sort of a similar idea. Now you have three constants: acceleration, the velocity, and the initial position are constants. So again, I've transferred this from s to x. And the same idea, if I know the time final, I can find my position final. And in a similar way, we can take this and then use calculus to do this too. So I know that the velocity in the x direction is dx dt, that derivative. And so in a very similar fashion to what we did last time, I can say dx equals v dt. And I can pull out some integrals, and over here I'll go from the initial position to the final position. Just like before, I'll go from 0 to t over here. Now, the only trick is that my velocity equation now, we just discussed, is equal to v0 plus a times t. So I plug it into there. Now this one we dealt with before. This is, again, when you have the integral of just d something, the antiderivative is just that something. So it's x evaluated from x0 to x final. And then this over here is going to be an integral of two pieces. So the first piece would be the v0 times delta t. And then over here, a times t delta t. Now this is the same situation we've been dealing with. The v0 is a constant. I can pull it out. And so that'll just leave me with v0 times t evaluated from 0 to t. And then this guy over here, the antiderivative of t, that's just a simple polynomial, will be 1/2 a t squared. And I should probably just be careful and call this t final. So this evaluated from 0 to t final. And when we are all done with that, over here we get x final minus x initial equals v0 times t final plus 1/2 a t final squared. Which again, if you just bring the initial position over to here, is the same equation as we got over here. And just to kind of explore this equation a little bit more, right? So this is how I would plot it. So hopefully this makes sense. You know, if I pick sort of 2 points on here and do the slope of the tangent line, you know, maybe this is point 1 and this is point 2. Hopefully you can see that point 2 is steeper, and so this here reflects the idea that the velocity is increasing, and it's also this you know, parabolic shape is basically saying that you're covering more ground every second. Okay, so because you're accelerating, in this case you're going faster and faster, so you'll be covering more ground every second. Of course, that comes from this sort of t squared term here. And so just looking at this dimensional analysis, I mean, first of all, hopefully you can see that the dimensions here, you know, meters per second times second, you know, gives us meters. And this one here, you've got meters per second squared times second squared, and that gives us meters as well. So both these terms are going to give us meters. And so what's happening is the v0 term adds on distance linearly, right? Every second you add the same distance. But the acceleration adds on distance by time squared. And it's just kind of like that picture we did before, where we were adding the area under the curve. It's kind of like another way to sort of think about it. But just in other words, if the object has acceleration, it's going to go faster each second it is moving, and it's going to gain more ground every second that it does this. All right, and so we've got our equations here, and so what I like to do is I like to have a separate one for x and y at this point in our life. Now here's our two equations. Now there's this third equation over here, And basically you can combine these two equations to get rid of the time. And so this is the time independent equation. So this is one, basically if there's no time mentioned in your problem, this is usually a good one to go with. Okay, so if like they don't give you the time or they don't ask for the time, then this is a good first kind of equation to deal with. So a lot of you have probably seen these before, but the big thing now once you have these equations is just figuring out which one to use, what is the circumstance you're looking at. So we'll do that next, but this is a good to kind of go through and develop these equations. And of course we have the same thing in the y direction, right? And so it just kind of depends. You could even call everything the x direction, but eventually we'll be dealing with problems that have an x and a y. So it's kind of nice to develop that now.